Hi everyone, welcome back to Lulumath. This video is on transformations of functions from descriptions. And in past videos, we've taken equations and we've determined what the transformations are. Now we're going to be given the transformations and we're going to try to find the equations. So the transformations of functions part 5 video talks about all 4 transformations in depth. We're not going to go into depth about why the transformations are the way that they are in this video. So if you need a refresher, make sure you check that video out. So just a reminder that our general equation is y equals a times f of k multiplied by the quantity x minus d plus c. And the a represents a vertical stretch or compression as well as a vertical reflection or a reflection in the x-axis. K represents a horizontal stretch or compression or a horizontal reflection, which is known as a reflection in the y-axis. And just a reminder that the scale factor is always 1 over k. D represents a horizontal translation. And C represents a vertical translation. And a super important thing that we can never forget, I can't stress this enough, is that K has to be factored out. So this K right here is multiplied by the quantity x minus d. This d will only be an accurate d if the K value is factored out. But sometimes that K is distributed through, so we have to factor that out. So be careful about that. All right, so let's get right into it. Find the equation of f of x, which is an absolute value function, after performing the transformations listed below on the parent function. Then we're going to determine the domain and the range of f of x, but notice we're not going to graph it out because we're going to use our understanding of the transformations to determine the domain and range without even actually graphing out the function. So first of all, our parent function, because it is an absolute value function, is f of x equals the absolute value of x. And just a reminder that the general equation with the transformations is as follows. And I've color-coded these on purpose so we can see where these descriptions are going to affect our values. So the first thing we're told is that we have a reflection in the x-axis. Well, if we reflect something in the x-axis, that is a vertical reflection, and that is going to affect the a value. We're also told that we have a translation 3 units up, and our vertical translation comes from the C value. And we're also told that we're translating 4 units to the left, and that will affect the D value. We also know that we have a vertical compression, so that will affect the A value again, with a scale factor of 1/2. And we know that we have a horizontal stretch, which is going to affect the K value with a scale factor of 3. So let's identify all of these values, A, K, D, and C, so that way we can write our equation. So because A is a vertical compression with a scale factor of 1/2, and because we have a reflection in the x-axis, A will be negative 1/2. To find K, we know that we have a horizontal stretch with a scale factor of 3. So since our scale factor equals 3 and our scale factor is 1 over K, then we just do the reciprocal. And the reciprocal of 3 over 1 is 1 over 3. Now we can also just cross multiply right here. So we would multiply K times 3 gives us 3K, 1 times 1 gives us 1. To isolate the K, we would divide by 3, so K is equal to 1/3. So that's another way to look at it. So here we can say K equals 1/3. Now, because D is 4 units to the left, we know that D is equal to negative 4. And because we know that we're moving 3 units up, we know that C is equal to positive 3. And we know that our function rule is the absolute value. So putting it all together, we'll be able to say that y is equal to negative 1/2, because that's what a is equal to. And then our function is the absolute value of, now we know our k value is 1/3, so we're going to say 1/3 multiplied by the quantity x, and then because this right here is minus d and d is negative 4, the minus the negative becomes a positive, so this will become plus 4, and we'll close our bracket, and then we'll close our input, which is 1/3 times the absolute value of x plus 4, and then we know that our C value is positive 3. So this is the equation of our transformed graph. Now you also are allowed to distribute that 1/3 through if you'd like. So if you do so, when you distribute that 1/3 through, 1/3 times x is 1/3 x, And then 1/3 times 4 is 4/3. And I'm specifically not writing the 4/3 in green because 4/3 is not our D value. But either one of these equations is totally acceptable. Now let's talk about finding our domain and our range. So if you remember, our general sketch for our absolute value function is going to look like this for the parent graph. Now, if we have a reflection in the x-axis and a vertical compression with a scale factor of 1/2, our graph will be shorter, but also reflected in the x-axis. We've got a vertical reflection. So we finished this point and this point. Now, if we have a horizontal stretch with a scale factor of 3, that means that my graph is going to get stretched out horizontally. So this is how it would look. That's what this will be. So we're done with that step. And then we are going to take our whole entire graph, so we'll move it from our vertex 3 units up and 4 units to the left. So our new vertex will move from this point right here to this point right here, but the width of our graph is going to be just like this blue graph that we have here. So this right here is f of x. And I apologize, this should actually say f of x here because the instructions told us to find an equation for f of x. So based on that, we can find our domain and our range. Now for our domain, for absolute value graphs, no matter what our input is, we will always be able to get some output. There's no restriction for absolute value graphs. Also, our graph goes to the left and to the right to infinity in both directions. Therefore, our domain is going to be x is an element of the reals. And then for our range, there are a couple things that we need to take into consideration. First of all, our graph was reflected. So now we have an upper limit as opposed to an original lower limit. But also the vertex is at -4, 3. So we know that our graph is not going to go above this 3 that we see here. So for our range, we can say y is an element of the reals such that y is less than or equal to 3. And in interval notation, we can say from -infinity to +infinity for our domain. And for our range, we can say it's from -infinity to +3. But the goal is to get to a point where we can identify this information without even having a visual. So we know absolute value graphs will always have a domain of x as an element of the reals, because no matter what x value you plug in, you can always find the absolute value of that x value, even if there are transformations done to that x value. For our range, we have to think about where our graph is moving and whether or not it has been flipped. So because we have a reflection in the x-axis, we now go from having y being above a certain point to y being below a certain point. Also, that vertex moved from 0, 0 to this 4 units to the left tells us that our x value will be -4, and this 3 units up tells us that our y value will be +3, and that's how we know that y has to be less than or equal to +3. In our next example, we want to find the equation of g of x, which we're told is a square root function. So this will tell us what our function rule is after performing the following transformations listed below on the parent function. And then we're going to determine the domain and the range of g of x. This one has a few tricky things that I want you to be extra careful of as we go through it. So we know that our parent graph is going to be the square root of x. And we also know that the general equation of a function is as follows. So we will go through our list here and see how these 3 transformations are going to affect our a, k, d, and c values. So first thing we're told is we have a reflection in the y-axis. Well, a reflection in the y-axis is a horizontal reflection because our graph goes from one point on the y-axis to the other side of the y-axis. So if you see it's moving horizontally, it's reflecting horizontally. So our horizontal reflections are going to tell us what the k value is. We also know that we have a translation 2 units down, and the c value tells us that. And 5 units to the right, and the d value tells us this. And we also know that we have a horizontal stretch, which is also going to affect our k value with a scale factor of 2.5. So where's the a value? Well, we don't have any vertical stretches or compressions or any vertical reflections. So for our a value, it's the same. Nothing is changing. So when we multiply, to keep our numbers the same, we multiply by 1. So like 5 times 1 is still 5. 1/3 times 1 is still 1/3. So multiplying by 1 doesn't change anything. So that's why our a value here is 1. It's the multiplicative identity. Now, because we are told that we have a horizontal stretch with a scale factor of 2.5, and we know that our scale factor is equal to 1 over k, then we know that 1 over k is equal to 2.5. But here's the thing, if we're talking about reciprocals, it's easier to write this 2.5 as a fraction. So 2.5 is equal to 2.5, and as an improper fraction is equal to 5 over 2. So we can say that 1 over k is equal to 5 over 2, which tells us that k is the reciprocal of 5 over 2. So k would have to be 2 over 5. Again, you can just cross multiply. So k times 5 is 5k. 1 times 2 is 2. Divide both sides by 5 and you get k equals 2/5. But we're also told that we have a reflection in the y-axis. So because we have a reflection in the y-axis, our 1 over k is actually going to be equal to negative 2.5 or negative 2.5 or negative 5 over 2, which means that k is equal to negative 2 over 5. For the d value, we look here, we're told that the graph moves 5 units to the right. So d is equal to positive 5. And for the c value, we look here, it's a translation 2 units down. So c is equal to negative 2. Let's go ahead and plug in all this information. So here we're going to use g of x because that's what we're asked to use in the question. And the a value here is 1. And since the parent graph is the square root of x, this f right here, our function rule is to take the square root of this k times x minus d. So our k value here is negative 2 over 5. And then we're going to write multiplied by x. And then here our d value is 5. That will preserve this minus sign. It doesn't change into a plus sign because we're not subtracting a negative. We're just subtracting 5. So this will say minus 5 here. We'll close our bracket and we're done with the square root piece. And then the minus 2 just tags along at the end. Now this 1 here is not necessary. I'm going to get rid of it. And this is our function. But just a reminder that we can also distribute this negative 2/5 through. So g of x could also be equal to the square root of negative 2/5 x. And then when I distribute this negative 2/5 through to this negative 5, I end up getting a positive 2. And I'm not going to write this out in green because the 2 is not the d value. And then minus 2. So this is our graph right here. Now let's talk about the domain and range. I'm going to explain to you how to find it without having a visual. And then after we talk about that, I'm going to show you visually why our domain and range are correct, okay? So for our domain, if you remember, our original domain of our parent function was x is an element of the reals such that x is greater than or equal to 0. But for our new function, we know that we have a reflection in the y-axis. So now instead of being greater than or equal to 0, it's going to be less than or equal to 0. It's going to switch to the other side. And we also know that our graph is going to move 5 units to the right. So instead of having a 0 here, it's now going to be a 5. So our new domain is going to say x is an element of the reals such that x is less than or equal to 5. Or we could say it's from negative infinity to 5, including 5, but not including negative infinity. Now for our range, if you remember, for our parent function, our range was y is an element of the reals such that y is greater than or equal to 0. We don't have any type of vertical reflection, but we do know that our graph has translated 2 units down. So instead of greater than or equal to 0, it's going to be greater than or equal to negative 2, but it's still going to stay greater than or equal to because there's no reflection. So here we're going to say y is an element of the reals such that y is greater than or equal to negative 2. Or in interval notation, we can say from negative infinity to negative 2, including negative 2, but not including negative infinity. But I just want to give you a visual on why this domain and range is accurate. So if you remember, our parent graph f of x equals the square root of x looks as follows. But we have a reflection in the y-axis, so that means our graph will flip horizontally. So this blue graph is what our graph will look like, but it's also going to have a horizontal stretch with a scale factor of 2.5, so our graph will stretch out horizontally as follows. We also know that our graph is going to translate 2 units down and 5 units to the right. So this point of 0, 0 will now move because our graph will go 2 units down and 5 units to the right. This is our new quote unquote 0, 0. So this is 5, negative 2. And if you can see here, all my x values will stop once we hit 5. So it's from negative infinity to 5, or any value less than or equal to 5. And our y values will not go below this negative 2. And that's why y is greater than or equal to negative 2. That's it for this video. If you have any questions, let us know in the comments below or at lulumath.com, where you can find blank or completed notes for this video. If you found this video helpful, please make sure to subscribe and share with others. Thank you, and we'll catch you next time. Bye.